What's up, everyone? How are you? Today, we're talking about nuclear chemistry. Now, this type of chemistry is special, it's relatively new, and it has given birth to a lot of different areas in medicine, in making of bombs, in making of energy. It's a huge area and it's centered around a different type of chemistry, centered around the nucleus. And today we're going to talk about it, look at what makes it different, what makes it dangerous, what makes it not dangerous, what makes it good for environment, and how it's used to make different things from bombs to energy. We're going to look at a few reactions that are involved, and we're going to look at a few calculations. And by the end of this video, you should be able to know how to do all of that. So let's jump into it. So the nucleus, radioactivity, and nuclear medicine. So let's talk about radioactivity first. Radioactivity is a process by which atoms emit energetic particles, and these are the particles that we're going to talk about. And when we emit those particles, we call them radiation. Right? So in the nuclear symbol, so we have a way to write down nuclear symbols, and this is what we use. We use the symbol of the element, and you might be familiar with this if you remember from the first chapter, second chapter, I think. So you have the symbol of the element from the periodic table. Down here, you have the atomic number, and up here you have what? The mass number, right? All of these you can get from the periodic table. Now, I want you to see something different. So here, boron has 11 as the mass number and 5 as the atomic number. But remember that when we talked about isotopes, we say that some isotopes of boron can have a different mass number. So instead of 11, sometimes you have some that have 10. All right. So how is that different? It's different because remember that the differences in mass number, the differences in isotopes come from the differences in neutrons. So we're talking about the nucleus here. So let's go back to the structure of the atom. This is an example of the atom, and this is nitrogen, right? Look at how nitrogen, you have electrons on the outside, and then on the inside, in the nucleus, you have the neutron and the proton. So usually the normal chemical reactions involve what? They involve electrons, and they involve the either giving, receiving, or sharing electrons. These are the bonds that we talked about. But the nuclear reactions go into the nucleus. Now we're talking about neutrons and protons instead of talking about electrons. So these are the nuclear symbols. That's what makes them different. So going back to the isotopes, let's look at the isotopes of carbon, for example. So your normal carbon has the mass of 12. That's why we call it carbon 12, right? So go back to the periodic table, carbon has 12. But some carbons in nature have 13 or 14 the mass. What does that mean? It means that whereas the normal carbon has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 has 8 neutrons. So you have a different number of neutrons, and we call these isotopes, and we'll talk more about why. So why do isotopes matter? It's because some isotopes are unstable. So a lot of isotopes are stable, but some isotopes are unstable, and the unstable isotopes produce radioactivity. So these are the radioactive materials. Whenever somebody tells you that something is radioactive, you know that it's an isotope that is unstable. And whenever they do that, whenever they are unstable, they emit particles. They emit different particles coming from where? Coming from the nucleus. So there are different types of particles that they can emit, but the main ones are alpha, beta, and gamma. And let's look at how different they are. When we emit alpha particles, what it means really means that we've emitted what? We've emitted 2 protons and 2 neutrons, right? So it's the same as the helium nucleus. What does that mean? It means that the alpha symbol is just for 2 helium, right? Alpha symbol here, which is a particle, which is a nuclear particle, is 4 2 helium. That's how you write it down. What about beta particles? Beta particles is when you emit a neutron converted to a proton. So you're emitting 1, right? And what's the symbol for beta? It's 0 and -1 beta. These are beta particles, and these numbers are really important. Remember, we're still using the symbols, right? The top here is the mass number, the bottom here is the atomic number. What about gamma rays? Gamma rays are a little different because they are really energetic and they're just pure energy, and they only have 0 here and 0 here. And this is the most penetrating form of radiation. This is the most energetic form of radiation. So one of the questions that I like to ask is, what's the most energetic particle between alpha, beta, and gamma? And gamma is the most energetic. All right. So all of these produce what we call ionizing radiation. Why is it called ionizing radiation? Is because whenever it goes through something, it creates ions, creates a trails of ions. That's why we call it ionizing radiation. And this penetrates through pretty much almost anything. And it depends on the energy, right? So gamma rays that we just talked about that are the most energetic have the highest penetrating power. Beta are in the middle, alpha are the lowest. All right, so we just talked about how your normal atom is going to emit, if it's unstable, it's going to emit a particle, and it can emit alpha, beta, gamma, or another particle. So when that happens, a nuclear reaction has occurred, and we can write it down as a nuclear equation. And nuclear equations are really different from your normal chemical equations, but you have different some rules that are similar. So this is an example of a nuclear equation. This is called alpha decay. Why is it alpha decay? Because we're producing alpha. So remember, 4,2 helium is an alpha particle, right? So we're producing helium. So uranium, that's 238 and 92 uranium, will give you a alpha particle plus thorium. So I want you to pay attention to this. 92 here is equal to 90 plus 2. That's the rule. And then up here, 238 is equal to 234 plus 4. So that means that the sum of the numbers on this side is got to be equal to the sum of these numbers, right? Why is it important? It's important because if I give you an unknown reaction and I ask you to complete it, you got to remember that. But let's look at another example. What if you have beta? The beta decay gives away 0 and -1 here. 0, -1 E, this is beta decay, right? And again, look at this. 16, you have 16 here, you have 16 plus 0 here. You have 7 here, you have 8 minus 1 here. So you have 7 on either side and 16 on either side. Really, really important to remember because it's going to come back. If you have gamma radiation, because again, gamma has 0 here and 0 here, we won't really change. We won't change anything. All right. But this is what I was telling you how it's important. I can tell you like, hey, uranium goes through beta decay. What does it give us? This is beta decay. You have uranium. Then you're like, okay, I'm going to calculate X. What does it give us? Right? So if you have 239 here, you have 0 here. What do you mean? What does it mean that you have here at X? You have 239 because it needs to be equal. What about down here? You have 92 here. You have -1 here. What number do you put here so that it will be equal to 92? You put 93 here. Why? Because 93 minus 1 is equal to 92. They have to be equal. So this is a good question that I can ask you where I give you an unknown compound. And another thing too is like, okay, let's say you wrote down 239 and 93 and you don't know the symbol. This 93, all you have to do is go back to the periodic table and find out where 93 is. All right. So if you go into search, locate 93, down here you see that you have neptunium as 93. So that's where the NP is going to come from. All right. So the numbers, and then the bottom number will give you the symbol. Very, very easy, but that's something that you need to know how to do. Now, another thing that we need to know how to do is find the half-life. What's the half-life? The half-life is the time required for 1/2 of a given quantity of substance to undergo change. What does that mean? It means that a half-life is the time required to lose 1/2 of anything. That's it. If you have 100 milligrams of caffeine in your body and it takes 5 hours to lose half of that, that's your half-life. Half-life of caffeine will be 5 hours. So half-life is the time it takes to lose half of anything. So this is an example of different radioactive materials. The reason why we care about half-life when it comes to radioactive materials is because some of them are really stable and take a really, really long time. We're talking about millions of years, and some of them are very, very unstable and they take just milliseconds, right? And those ones that are unstable are the ones that are used, for example, to produce bombs and energy, and the ones that are really stable are the ones that we use, for example, to do carbon dating, because we know that they take a long time to degrade. So these are examples from 5 to 6,000 years on carbon-14 to uranium that can take 710 million years. And the half-life, this is a typical example of half-life. So the half-life here is 6 hours. So after 6 hours, look, after 6 hours, you have half. After another 6 hours, you have half of that. After another 6 hours, you have half of that, right? So it's really, really easy to calculate half-life when you understand what it is. Let me give you an example. So let's say I'll tell you that half-life of carbon-14, this is an example, is 5 years. It's just a random example, right? And then I asked you, like, how long it take, this is really hard to write, give me a second. How long will it take for for 100-gram sample to become $12.5. All right. So pretty much, if the half-life is 5 years, how long is it going to take for something to go from 100 to 12.5 grams? All right. Now that might seem hard, but I'll show you how really easy it is. Okay, so if half-life is 5 years, if the half-life is 5 years, that means that we're going to start with 100 grams, right? Start with 100 grams. That's okay. Now, in 5 years, how much are we going to have? In 5 years, you're going to have half of that. That's how the half-life works. In 5 years, you're going to have 50 grams. That's 5 years. In another 5 years, we're going to have what? 25 grams. Because it's a half-life, right? And then in another 5 years, look at what we're going to have. 12.5 grams. So how many years did it take? 5 plus 5 plus 5, that's 15 years. So these are calculations that we do when it comes to half-life, right? So it's pretty easy when you understand what a half-life is. So I can give you another example here. It says a patient receives 10 nanograms of radioactive with a half-life of 12 hours. Okay. How much will remain in the body after 2 days, assuming the radioactive decay is the only path for removal of the isotope from the body? All right, so let's just calculate it the way I just showed you how to calculate the other one, right? So you start with 10 nanograms, right? And then I'm asking you, how much will remain in the body? Well, look at this. You start with 10 nanograms. 10 nanograms, right? And then it has a half-life of 12 hours. So after 12 hours, we're going to have 5 nanograms, all right? After another 12 hours. So they're asking 2 days. So 2 days, 1 day is 24 hours. So 2 days is 48 hours. So after 12 hours, 5 nanograms. After another 12 hours, you have 2.5 nanograms. After another 12 hours, you have 1.25 nanograms. All right. So that's 36 hours. After another 12 hours, you have 0.625. 0.625 nanograms. And that's what's going to be left after 2 days. So that's pretty much how we calculate half-life. So let's look at another example. Another example is, what is it saying? A patient received 10. This is the same question, and they got the same answer, but it's pretty much what I just showed you. All right. So I'm going to show you an equation that you can use to pretty much calculate any half-life problems, and this is it. So to find the remaining quantity, you're going to start with the initial quantity times 0.5 to the number of half-lives. All right. So this is a formula that shortcuts what we just did here. So for example, here, 2 days has 1, 2, 3, 4 half-lives. So you have 4 half-lives here. So n will be 4. So if you want the remaining quantity, will be the initial quantity, which was 10 nanograms, times 0.5 to the 4th. So this is a general formula to calculate half-life. But if you understand it, you can also use this process of just, setting it down. But imagine if I ask you like 100 half-lives, you will just keep writing until night. So that's why I give you a formula that you can use, so that if I say 100 half-lives, you put 100 up here in place of n, and then mi is what you start with, mf is gonna be what you are left with. All right, that's pretty much what half-life is. You're definitely gonna get questions about calculating the half-life. So how do they measure radiation? Well, they use what we call a Geiger counter, and the Geiger counter, it works very easy. It's pretty easy to use. I won't talk into it, but it uses the voltage and how the radiation is going to affect the voltage. So you've heard in the movie how they kind of scratchy sound that it makes when it gets next to the radiation. That's pretty much the change inside, but I won't talk too much about it. We measure radiation in Curie's, and this is from Marie Curie. You might have heard of her. She's one of the pioneers of radiation, which unfortunately killed her. But this is a unit. You have a unit that's Curie. You have Becquerel is another one. You use Röntgen is another one. REM is one that we use. LD50 is another one. You can look at the different definitions here on screen, but I won't talk too much into them. We're going to use another one called, the one that we're going to use a lot is REM. So that's the one that I'm going to use. And with that being said, is radiation dangerous? Radiation is very dangerous, but how dangerous is it? Well, if you are exposed to a high dose of radiation, first of all, you're gonna die right away. But depending on the level, sometimes you might just die slowly. Your cells are going to start to die, and then in turn your organs are going to start to give up, and your body is going to start to give up. So depending on the level of radiation, you might die instantly, or people sometimes have taken months and even years to die. It can also just not affect your cells and organs, but change your DNA so that it causes cancer and other things. But how much do you need for you to be worried? Because a lot of things are radioactive, and I'm going to go through a few of them. So let's look at a few natural and not natural radiation that we are exposed to every day. Because believe it or not, you're exposed to radiation every day. So cosmic radiation is the one that we experience all the time. This comes from the stars and the galaxy, but it's very low. It's about 50 mrem, which is really low, 50 to 100 a year. And I'm going to be looking at the things that we are exposed to a year, and then I'm going to add them up to see how dangerous really they are. Terrestrial radiation, radiation from different things on Earth, uranium, thorium, can range from 200 to 1,000 depending on where you are. So if you live in Brazil, for example, or India, you can be exposed to up to 1,000 mrem, but that's nothing. I'll talk to you about how those are nothing. Food that you eat also contains radiation. You've heard that banana contain radiation, and other food, they contain potassium and carbon 14 and other radiations. But again, if you add them up, they're going to be like 20 mrem per year. Not very significant. You even in your body, you have radioactive material, potassium, carbon, and other radioactive materials. We have them in our bodies as well. And also some other things like nuclear weapons, fallout from a long time ago. Watching TV will also give you some sort of radiation. Living close to a nuclear power, all of these will give you a low level of radiation. If you have a pacemaker, it's going to contain some level of radiation. X-ray, when you do an X-ray, you're going to be exposed to some radiation, but again, very, very low, right? Every X-ray every X-ray test is going to be a low dose of radiation depending on what you have. So if you add them up, is radiation that we are exposed to really dangerous? No, right? Your average US citizen is exposed to about like 360 mrem a year. And look at this. Your chance of dying from cancer will increase if you have 250,000 mrem a year. So that's thousands of times more than what you're exposed to. So you have to be exposed to a lot of radiation for a lot of years. Right? So you're really safe from all of these radioactive materials that are around us. You will have to pretty much live close to a bomb or another really, really radioactive material in order to start suffering from all of this radiation. So where else do we use radiation? We use radiation in health, in medicine. We use it a lot in imaging. We use it a lot in even treatment of different types of cancer, believe it or not. We use it in energy, so you have a lot of nuclear energy. You've seen these around, right? Nuclear reactors that produce energy. You even have some that are used in the industry to make some stuff. Used everywhere. Now, it's also used to make bombs. So nuclear fission is a way to make bombs by breaking the nucleus. So the type of the radioactive reactions that we looked at produce different types of bombs, nuclear fission. Another form of radiation is nuclear fusion, which is fusing nuclei, which also produces even more energy. That's how your sun works. The sun works by nuclear fusion, right? So a sun is also a nuclear reactor. So this is another use of radioactivity, producing tons and tons of energy in terms of either bombs or in terms of producing energy to power our homes. So it depends. You're going to choose what you use it for. And that's enough for nuclear energy. Another thing that I would talk about is nuclear waste is very, very hard to get rid of because, again, we talked about how uranium takes 700 million years to decay just to be cut in half. That makes nuclear waste almost it's pretty much impossible to get rid of it. If you might bury it, you might put it anywhere, it still won't decay. It won't go anywhere, but it will still be dangerous. So there's a big problem of nuclear waste, and that's one of the obstacles for producing nuclear energy because in theory nuclear energy is very clean, right? It doesn't emit any bad material, so it's clean energy, but the waste is really hard to get rid of. But other than that, you should be able to, now you should have an idea of what nuclear reaction is and what radioactivity and nuclear medicine, what all of these are. Now, I just wanted to remind you that you should be able to calculate, right? You should be able to calculate half life, and you should be able to calculate, you should be able to do reactions. You should be able to do nuclear reactions. Let me just go back to kind of recap. You need to be able to, if I give you a reaction like this, to find out what X is. And also you need to use this equation to find different levels of half-life. But make sure that you know all the other things that we talked about as well. And you're always welcome to reach out to me whenever you have a question. And I think that's enough. That's enough that I'm going to talk about. And I'll see you next time.